So here's an example.
So very difficult.
Consider a vertical column of length L, that would be this, that's hinged at both ends and with a constant vertical compressive force, pressure that is, P, applied to its top. The boundary value problem governing its deflection y of x is EI times the second derivative plus PY times the function itself is equal to 0, with y of 0, 0 and y of L 0, where E is constant involving the elasticity of the object's material, and I is the moment of inertia of a cross-section about a vertical line through its centroid. Here's a picture of the situation, right? We got a beam, we got pressure on top of the beam, and the beam deflects. This is previously described situation if C equals P over E times I. So then y double prime plus Cy is equal to 0 with our boundary conditions as stated. So we either have a deflection curve y equals 0, means it doesn't bend at all, or y equals a times the sine of n pi times x, corresponding to the eigenvalues n squared, pi squared over L squared, etc. So you can figure out what they are. Therefore, the column will buckle only if the pressure on the column is one of these values. And those are called critical loads. Oh yeah, EI load. Now I get what you were saying before. The deflection curve corresponded to the smallest critical load, called the Euler load, and that's pi squared times E times I over L squared. And that deflection curve would be sine of pi times x over L, and it's known to be what's called the first buckling mode. If a restraint is placed on the column at x equals L over 2, in other words the halfway point, as in this picture shows, you put some kind of restraint here, then what happens is you would move the smallest critical load would be then P equals 4 pi times E times I over L squared, and the deflection curve would be as in this figure right here. And if we place restraints where x equals L over 3 and 2 over 3, in other words, third of the way and 2/3 of the way, then the critical load becomes like the third eigenvalue, and so on and so forth for other values of n.
We better put on our flanking caps and think hard.
Yeah, we better.